Uh, a very good afternoon to one and all present in this online FDP 2020-22. I, Himanshu Deka, Assistant Professor of Faculty of Pharmaceutical Science, Assam Downtown University, would like to welcome you all to this online FDP 2020-22. Today, we have with us Dr. Kunal Roy, sir. The sir will be delivering his lecture on the topic chemical read across prediction of ecotoxicity data. Now, I would like to request our Honorable Dean, sir, Dr. Biplab Kumar De, to welcome our speaker. Sir.
Yeah, thank you, Himanshu. At the very outset, a very good afternoon to one and all present out here. Of course, the gathering participation is likely to increase very soon. I heartily welcome Kunal Roy sir for sparing his invaluable time with us, and I'm sure that all the researcher, faculty members, and PhD scholars, whoever will be participating in this FDP and this particular talk, they are definitely going to get all the recent and fitting information about the advancements and in research academics post-pandemic era. And this is the first time I think Kunal Roy sir is there with us. Of course, it is in virtual mode, but we are really confident to have you with us in physical mode also, sir, down the line. So with this, without wasting much more time, I would request Kunal Roy sir to please start your talk. Thank you.
Thank you very much. Good afternoon to all. I think the slides are visible.
Yes, slides are visible, sir. Okay. Roy, sir, so with your permission, I would like to give a brief outline about you to the participants, sir.
Okay, give a brief one.
Yes. Yeah. Okay, sure, sir. So, as you know, our today's speaker is respected Dr. Kunal Roy, sir. Sir is currently holding the position of professor in the Department of Pharmaceutical Technology in Jadavpur University. Sir has been a recipient of Commonwealth Academic Staff Fellowship and Marie Curie International Incoming Fellowship from Manchester University. Besides this, sir has also published more than 350 research articles in various reputed journals, and also has many book chapters and various books in reputed publication house. Sir has also participated in EU-funded project. Apart from this, projects are also a part of various national government-funded projects. So with this introduction, I would like to request Dr. Kunal Roy, sir, to start your presentation. Sir.
Thank you very much for the introduction, and I'll go to the topic now. This is chemical read across predictions of ecotoxicity data. I think many of the participants will have idea about QASR, quantitative structure activity relationship studies, which are actually supervised learning process of statistical model development. But today, I'll talk on read across, which is another similarity-based method, but originally this is unsupervised in nature. This is not statistical model development, and there are some advantages of read across predictions over QASR, especially dealing with smaller data sets to bridge the data gaps. So mainly read across has been applied in regulatory toxicology for predictions of various toxicity endpoints, but this can as well be applied to prediction of various property endpoints and biological activity endpoints in drug discovery paradigm. Now we are surrounded by a large number of chemicals around us, which starts from various domestic chemicals like biocides, cosmetics, pharmaceuticals, to various industrial chemicals and various chemicals of emerging concern. So as we are exposed to all these chemicals in our day-to-day life, and not only humans, but these chemicals affect different organisms of diverse trophic levels in the environment. So these are a matter of concern about the effect of these chemicals on human and environmental health. So it is required to evaluate the risk and hazard potential of all these chemicals from environmental health point of view and human health point of view. Now, since there is a large number of chemicals currently in common use and new chemicals are registered at a very high rate, and we have very limited resources to evaluate experimentally the hazardous potential of all these chemicals against thousands of different endpoints. So it is obvious that we cannot get experimentally even the basic information of environmental fate and effects of all these chemicals. At least we have experimental data for less than 1% of chemicals available. So it is necessary to develop some kind of in silico models which can accurately and rapidly predict environmental behavior of these chemicals. The in silico methods are time and cost effective. They avoid animal experimentation and they can comply with the ethical requirements. They support free principle replacement, production, and refinement of animal experimentation. They can be applied for virtual compounds, and this kind of modeling techniques are supported by various regulatory bodies and legislations, including European Center for the Validation of Alternative Methods, International Organization of Medical Sciences, REACH regulation, US EPA, and Organization of Economic Development and Cooperation. Now, coming to read across, I told that I would discuss on read across today. So this is a prediction method using similarity principle. It uses some known chemical analogs, which are structural similarity to chemicals for which we need predictions. So we have to do this prediction from same chemical category. Read across is accepted by REACH and US EPA. It can be used for data gap filling, and we need a defined chemical category for read across predictions. Now, read across can be of two types mainly. One is analog approach, there is category approach. Now, in analog approach, we may have very limited number of source chemicals, and in case of category approach, will have a handful of source chemicals. Now, as you can see, this read across prediction can be of interpolation type. That means when the query chemical will be within the descriptor space of source chemicals, or it may be extrapolation type. That means it is away from the descriptor space of the source chemicals. And we may have some outliers also in such approach. Now, what do we mean by similarity? Now, we represent chemical structure information in the form of some diagram or picture. And we can encode the structure information in different dimensions, like 0D, which does not consider even the molecular structure. Molecular formula is sufficient for 0D kind of chemical information depiction. It will be 1D, maybe fingerprint type. It will be 2D, from two-dimensional rough theoretical representation. It will be three-dimensional representation of molecular structure. It will be 4D, where we can also include conformational aspects. There will be higher dimensional aspects also. But in all the cases, the information encoded in the chemical structure should be converted into some numerical quantities so that we can do some numerical manipulations. So these numerical quantities are called descriptors. And then we can apply some feature selection and appropriate algorithm, model development algorithm, maybe of classification type or regression type, depending on the type of endpoint data available. We can do modeling, and we can finally predict the endpoint. This is the basic workflow of any predictive modeling analysis. Now, if we take some very simple examples, some simple compounds like ethylbenzene, nitrobenzene, chlorobenzene. Now, how they differ from each other. So we can describe their difference in structural feature in various forms. We can take, say, molecular weight. We can take their log P value, or we can just describe the number of carbon atoms present, number of nitrogen atom presence, number of oxygen atom presence, number of double bonds presence. Or we may describe, say, some 3D information also. We can describe some quantum chemical information also, and some higher dimensional information also. But it is not required always to use higher dimensional information. So it depends on the requirement of the particular data set, the diversity of the data set, and requirement of the endpoint values. We may not need to use always 3D information. So 2D information is sufficient in most of the cases, and in several cases, the 2D structure derived information can supersede the quality of the model obtained from 3D information. Anyway, so first we have to do the data set processing, because there will be several intercorrelated noisy descriptors or constant value columns. We have to omit them, and we have to do the normal curation process, like normalization, standardization, and then feature selection and identification of outliers. And then we can apply appropriate modeling technique, which may be either regression based or classification based. And finally, we can check the quality of the model by various statistical quality and validation metrics. And at the end, when we get prediction, then if we plot the predicted values against observed values, we'll get a plot like this. It's called scatter plot. And for a good model, we can expect that the points will be close to the 45-degree angle line. I told that read-across is a similarity-based approach. Now, if we now define similarity, and for the ease of our discussion, if we consider that we have to describe similarity with respect to only one feature, that means we have only one independent variable or x variable. In that case, if we plot the endpoint y versus x, and it may so happen that our query chemical is in between the other two chemicals for which we know their endpoint values. So as based on the feature, this query chemical is close to the other 2 points. So this is the interpolation type of experiment. And we can actually find out the slope using the our basic knowledge of coordinate geometry. You can see we can define the slope between the points x2, y2 and x0, y0, and which we may equate to the slope for the points x1, y1, x0, y0. So if we want to draw a hypothesis for similarity of our query chemical, that is x0, y0, to the other available chemicals x1, y1, and x2, y2, then obviously we can draw a straight line, and I told that we can find out the slope from here, and once you get the slope, you can draw a line using the usual y equal to mx plus c. In other case, it will so happen that our query chemical is not within the feature space, it is beyond the space of the other 2 chemicals. So in that case, this extrapolation type. So we will find out the slope from the closer chemical, that is X1, Y1, from the expression, and then we'll use both the query chemicals to find out the value of we'll get the slope from the other two chemicals, and we'll use y equal to x plus c to get the endpoint value that's unknown for the query chemical. But this is a very simplest case where we have only one feature and only two similar available compounds. But the real life situation is not as simple as this. Now, we usually may have several other features based on which we have to derive similarity. So when we have many such features, then we may need to reduce our dimensionality. And to reduce the dimensionality, one most commonly used technique is principal component analysis, which is a data reduction tool, and which tries to identify the commonalities among the features available, and it reduces the higher dimensional matrix to a lower dimensional one without significant loss of information, keeping the explained variance intact. Now, if we take the first two principal components, which explain the variance most for the descriptor matrix, if we plot PC1 versus PC2, we can see such clusters. So our compounds can be clustered based on the information present within them. And from that, we can identify their similarity. That means compounds within the same cluster will be similar, but compounds with of different cluster will be dissimilar. In another approach, we can do self-organizing map, which is a machine learning technique, but this is unsupervised type. Unlike artificial neural network, we are not using here backpropagation technique. This is a compositic learning technique. And in the surface layer, we can project our compounds, and they'll be clustered, and the similar compounds will be in the similar cluster, or they will be near to each other. So from these, we can have some idea of similarity, but similarity can be calculated by several other measures also. Maybe some distance measure, which is opposite of similarity, or several similarity computing techniques. But we need to know that which are the features are important for discussing similarity among a given set of compounds. But we have to go back to QSR for some basic understanding, because ultimately we have to do predictions, and we have to evaluate the quality of predictions. I told that QSR is basically a statistical learning approach where we correlate the endpoint, which may be biological activity or toxicity or any other property, with descriptors which encode chemical information in numerical form. And we develop this relationship with the help of statistical tools. So the simplest model, regression type model, which is multiple linear regression type, will look like this, where Y is your biological activity or endpoint, and on the right-hand side, you have several X variables, X1, X2, X3. These are actually descriptors, but descriptors are not unknown. These are known quantities because structure is known. So unknown here is the regression coefficients, that is A1, A2, A3, and so on, which you have to find out by solving a regression problem. But if you are doing a classification analysis, in that case, your Y values are graded. That means active or inactive, toxic or non-toxic, and so on. So you have a binary type of endpoints. So you'll go for a classification modeling instead of regression. For checking quality of regression type of QSR model, usually we use metrics like determination coefficient. So that basically uses the concept of comparison of squared residuals. Residuals means the difference between the experimental and calculated values. So obviously, for a good model, the difference between experimental and calculated should be low. But how much low? So ideally, it should be zero, but there is no ideal thing. So it will be a non-zero quantity. Especially, we are taking sum of squares, so it will be a positive quantity. So we have to compare it with some reference. So there should be some reference. The reference here is no model. That is the mean value of the training set mean. So the difference between the individual experimental values from the training set mean, that will constitute a considerable quantity. So when you take sum of squares, so that will be a sizable amount. So this denominator will be always very high and numerator will be small. So small by high will be a small value. So when you take 1 minus this small value, that will be close to 1. So this determination coefficient value should be close to 1. So when you have R square close to 0.9, that means a good correlation. But the correlation does not ascertain the good quality of prediction because it doesn't contain any parameter which describes the number of descriptors you have used to derive the correlation. So a model with a higher number of descriptors is statistically less sound. So you may use explained variance of adjusted R square, where the metric is penalized based on the usage of higher number of descriptors. Then you have other metrics like variance ratio, which gives idea about the significance of the correlation coefficient value. Correlation coefficient means square root of determination coefficient, and also the stability of beta coefficients or regression coefficient. Then standard error of estimate, that is the square root of sum of squared residual divided by the degree of freedom. This should be a low value. The previous metrics do not say anything about the applicability of the model on new set of data. So for that, we apply the validation aspect. So validation gives us idea about the reliability of prediction, confidence of predictions. So this can be done majorly by two ways. One is internal validation, where we use the same set of data used for model development for checking the quality of prediction. This is done either by leave one out or leave many out approach by removing one or more of the training compound in different iterations and redeveloping the model from the reduced data set and predicting the compound, omitted compound from the model obtained from the reduced data set. And this we do by iterations. And finally, we compute the quality in terms of Q square, which looks like R square formula. We can do also external validation, where we use a separate set of data, that is test set, not used in model development, and we check their quality of prediction in terms of R square trait. Here also, the quality of prediction formula is similar to R square, but here the point of reference is training set mean. But when point of reference is test set mean, then that is called another metric, Q square F2. So this is Q square F1, this is R square Q square F1, and we may have also Q square F2. Also, you can do bootstrapping, that's a sampling procedure. We can do wide randomization, but I'm skipping those. If we see the steps involved in QSM model development, you'll see it starts from data preparation, processing, prediction, validation, and interpretation. So we have this is a ligand-based approach. We have to start with a set of known chemicals with known endpoint values and their known structures. So usually for biological QSR, you have to convert the endpoint values into log conversion. For some reason which gives the easily manageable range of data, and that is log those response curve is sigmoidal, middle point is linear, which is easier to model, etc. Then we have to convert the structural information into numbers. That is called descriptors. We have to formulate the QSR table. We have to train the QSR table by removing redundant, noisy descriptors, intercorrelated descriptors, by removing constant value descriptors, and so on. And then we have to divide the data set into training and test. Now, training set, this is used for model development, and the test set is unseen to the model. The test set compounds, although they have biological activity value, experimental values, but they are unseen to the model. The model is trained, or learning process is done only from the training set compounds, and model does not learn from the test set compounds. So when you have developed your model through feature selection process, then you have to apply the concept of applicability domain to understand whether your tested chemicals are within the domain or not of your model, and then only you can predict. And when finally you are applying your model on the tested data is unseen, but they have experimental values. So you are comparing your prediction against the experimental values. This is a material that whether this experiment has been performed before model development or after model development. But you are comparing your model derived predictions with experimental values. That gives you the confidence about the quality of prediction. So we need to derive different metrics that I have already discussed in external validation that will give us confidence what the quality of prediction and how much applicable the model is on new set of data. And when we are confident that the model is robust, predictive, then we can apply it to new set of data even without having biological activity values for prediction purpose. And the model can be used for interpretation, for mechanistic explanation, and for screening databases, and also for prediction and designing new chemicals. Now, why read across? I told that QSR is a very good tool, statistical modeling technique for prediction purpose. But the problem of QSR is that QSR is a statistical model development process. So any statistical model development process will have its own statistical requirements. That means it should have good degrees of freedom. So you should have more number of data points and lower number of descriptors. Secondly, you have to divide the data set into two parts, training and test. So actually you are not using some part of your data for your model development and learning process. So for a small data set, it remains really challenging how to deal with the problem. Because you have very small data set, then if you keep some compounds aside, not used for model development, used for prediction only, then the model is being developed only using a very small data set, which is statistically unreliable. So QSR may not be suitable for very small data set, where read across can do wonder. QSR is not suitable for small data set. Read across is not a statistical fitting process. Calculation is comparatively easier than QSR. Originally, read across is the unsupervised method. So it is used as an alternative tool for hazard assessment aimed at data gap filling. So actually, in industries for regulatory purpose, read across is used more than QSR for bridging data gaps for industrial chemicals. Now, if we take example of nanotoxicity, toxicity of nanomaterials, you know, usually nanomaterials are mainly of two types, that is carbon-based nanomaterials or graphene types and metal oxide nanoparticles. And these metal oxide nanoparticles are used in various applications, maybe in cosmetics, paintings, coatings, solar cells, and various catalysts and several other applications. So as they are used in varied applications, humans are exposed to those nanomaterials. And nanomaterials have their inherent toxicity to living organisms, not only humans, but also towards different species of diverse trophic levels. But in general, toxicity data of nanomaterials is very limited. For various species, usually it is 17, 18, 19, 20, which may not be very good for QSM model development. So read across comes here. We can use the similarity technique for predictions, and sometimes read across based predictions can supersede the quality of QSM models. So here we discuss about chemical read across predictions of nanotoxicity data with an objective to develop an easier and efficient method of quantitative read across predictions. So this can be applied for small data sets, and we can compare the results with previous methods. And we also developed an application, Java-based application for read across prediction. Here we take 3 different data sets, nanotoxicity data sets, toxicity of metal oxide nanoparticles to human keratinocyte cell line, PEC50 value of metal nanoparticles against E. coli and against E. coli under dark condition. And we have used the same descriptors as used in original publication. So the descriptors used here is not important. Here important is the algorithm development. So we used here the same original set of descriptors as used in the original publication. In all cases, the number of data points was less than 20. It was 18 or 19, like that. Now we divide the data set into sets, although it's not appropriate to term them as training and test. It's more appropriate to use source compounds and target compounds or query compounds. So query compounds are predicted based on the source compounds, depending on their similarity. So we have to identify the similar source compounds for each query compounds, and we have to identify those source compounds, and we have to define similarity based on different measures. We have used here 3 different measures: Gaussian kernel function, Laplacian kernel function, and Euclidean distance-based similarity. Now, based on similarity, we can sort the similar training compounds, and then we can give weightage based on the similarity level. And finally, we can do weighted average prediction for the query compound. So although the original read across is unsupervised in nature, here we are including some aspects, some elements of supervision for weighting purpose. The first, the similarity measure used here, Gaussian kernel function, which is based on Euclidean distance function. So this is actually the Euclidean distance between the 2 vectors of length n, and sigma is a hyperparameter which is to be optimized. So this is a machine learning approach of optimization of hyperparameter for this particular problem. Second similarity function is Laplacian kernel function, which is obtained from Manhattan distance between 2 vectors. And here gamma is a hyperparameter having different values, and one has to optimize this. And third one is Euclidean distance. So for this, prior scaling is required, prior scaling of descriptor values based on standardization approach using standard deviation and mean value of the source compound. And then we calculate the Euclidean distance, and then we scale the Euclidean distance between 0 to 1, and then we convert Euclidean distance to similarity, because similarity equal to 1 minus distance. So although we apply different methods of similarity calculations, so finally we predict the query chemicals based on weighted average prediction. And once we get the prediction, then we apply statistical methods to compare the quality of prediction, as we do in case of QSM. So this part is similar to QSM, that is the statistical model development, statistical analysis part. So we can use Q square F1 and F2, as I've already mentioned, as the metric for checking quality of predictions, and also root mean square error of prediction. This value should obviously low for good quality of prediction. But if we are doing classification-based prediction, we can also do classification, not only quantitative prediction. Even our the supplied values are quantitative in nature. If we want to get the prediction in qualitative sense, based on the training set mean as the threshold, we can classify our prediction as, say, higher active or lower active, higher toxic, lower toxic, and so on. So in that case, we can have a contingency table of, say, true positive, true negative, false positive, and false negative. So as you know, true positive means the positive compounds predicted to be positive. True negative means negative compounds predicted to be negative. False positive, that is predicted to be positive but actually negative. False negative, predicted to be negative but actually positive. So based on that, we can define different measures like sensitivity, specificity, precision, accuracy, and F measure, and other measures like G means, the Cohen's kappa and Matthews correlation coefficients. So these for classification predictions. So we have developed a Java-based application which can be obtained from this site free of charge. It needs the training set and test set data as input in Excel format. User has to provide the sigma, gamma value. If the values are not known, one can give value 1 for this. Number of similar training compounds, which should be up to 10, distance threshold and similarity threshold. The program generates 2 output files, one for biological activity prediction response, predicted response, and other is for sorted experimental response values with respect to distance and similarity. These are some snapshots from the program. Now, from an initial analysis based on Euclidean distance, you can find that in our 3 data sets, we had 9, 8, and 8 compounds in the query set. As you can see, this is a small set. So we have divided in a 50-50 base division. We have taken 50% compound in the training or source and 50% in the query. And if you see the Q square F1 and Q square F2 values, these values are more than 0.6 for data set 1 and 3, but not so in case of data set 2. But these results are without any optimization. Next, we go for optimization of various hyperparameters in the machine learning approach. And we see we vary the sigma values. And as you can vary sigma values in Gaussian kernel functions, the Q square F1 value changes. But when you sigma value is 0.75, for data set 1, you get the maximum value of Q square F1. When sigma value is 0.5, you get the maximum value of Q square F1 in data set 2. In case of data set 3, the maximum value when sigma value is 0.75. Similar way, we vary also the gamma value for Laplacian kernel function, and we get different requirements for different data sets. For data set 1, gamma equal to 1. For data set 2, gamma equal to 0.91. Gamma 2, and for data set 3, gamma equal to 1.5. We can also change the number of closed training compounds for toxicity prediction. So actually, although we can use up to 10 closed compounds, but all 10 compounds are not required. We can see that 2 or 5 compounds may be sufficient. So if we give lower number of compounds, that means a lower degree of noise is introduced in the weighted average prediction. So we can see that for different data sets, we may require different degrees of closed compounds based on Euclidean distance or Gaussian kernel or Laplacian kernel. For example, for data set 1, number of closed compounds 5 is sufficient for all 3 measures, Euclidean, Gaussian, and Laplacian. For all 3 metrics, Q square F1, Q square F2, and RMS. In this way, for other data sets, we may require 2, sometimes 5, or sometimes 4 as the required number of closed training compounds. This is a pictorial representation to show the requirements of different metrics where we get the maximum values depending on the different number of those training compounds. Then also we can vary the distance and similarity threshold. We can optimize them, and we can see that for data set 1, distance threshold 0.4 and similarity threshold 0.05 gives the best result. Q-score F1 is up to 0.96 in Euclidean distance, is the maximum. In case of data set 2, we get the maximum value in case of distance threshold 0.5 and similarity threshold 0. For Gaussian kernel function, you can see GK value, Q-score F1 value is 0.91. And third data set, we see when the distance threshold is 0.4 and the similarity threshold 0, we get the maximum value of Q-score F1 for Euclidean distance 0.96 Q-score F1. This is the maximum value. This is also shown by this radar plot for the three metrics. Now, if we compare the results for classification, because the previous one was for quantitative predictions. Now, if we see in terms of classification using training set response mean as the threshold, and if we classify predictions into two groups, that is toxic and non-toxic, we see that for data set 2 and 3, we get up to 100% sensitivity, specificity, accuracy prediction. The perfect prediction for data set 2 and 3, and for data set 1 also, we get for specificity and prediction 100% values. Now, if we compare these prediction results with previous read-across predictions and QSR predictions, we'll see for data set 1, previously, the read-across prediction showed Q-score F2 value 0.74, maximum 0.74, whereas here we have got from Euclidean distance similarity measure at distance threshold 0.4, Q-score F2 is 0.96. And from previous nano QSR, the Q-score F2 was 0.83, whereas presently is 0.96. So it is superseding the previous results. In case of dataset 2 also, from Gaussian and Laplacian kernel, we got Q-score F 2.91 versus previous quantitative read-across prediction from principal component only 0.80, and nano QSR previous report 0.83. In case of dataset 3, the Euclidean distance-based prediction shows Q-score F2 value 0.95 compared to previous quantitative read-across 0.91 and previous nano QSR minus 0.20. So we see in all three sets, we get better results in present read-across prediction compared to previous read-across prediction and previous QSR predictions, which is shown here diagrammatically also. So for these nano read-across studies, here we have developed a new quantitative read-across algorithm by optimization of different hyperparameters through a machine learning algorithm using Euclidean distance, Gaussian kernel function, and Laplacian kernel function similarity estimation. And one has to optimize the sigma and gamma values of Gaussian and Laplacian kernel functions. And number of closed source components has also be optimized. It should be 2 to 5 usually. And from this study, we see the distance threshold and similarity threshold can be optimized within the level of 0.4 to 0.5 for distance and 0 to 0.05 for similarity threshold. And the program is available from the link shown on the page. And this new similarity-based read-across algorithm and the design software is easy to use, efficient, and design expert-independent alternative method for prediction of metal oxide nanoparticles. Now we have also used this for other applications also, for other ecotoxicity and other kind of activity predictions. And here are some examples. Here, this is read-across prediction of soil ecotoxicity of Paulsonia candida. Now, soil ecotoxicity, it is an endpoint which is very seldom explored. It has not been explored to a large extent previously. So it is one of the first works of measuring soil ecotoxicity against Falsomia candida. That is an organism which is considered as a model organism for soil health. So here we have taken the soil ecotoxicity data, and we have divided the data set into two parts, training and test, using a 75%, 25% division. And then the training set is also divided into sub-training and validation set. And we have optimized different hyperparameters based on the prediction for the validation set here. And finally, we have used the optimized setting for the whole training set and used for prediction for the query compound or test set. And we see the quality of prediction is good in terms of Q-square F1 and F2. Q-square F1 is 0.76, Q-square F2 is 0.70. And these values are actually better than the quality of prediction in case of corresponding QSR models. And here Gaussian kernel function is the winner. We have also used this for read-across prediction of androgen receptor binding affinity. So this is relevant for endocrine disruptor chemicals or pharmaceuticals and for ecotoxicological threat. So we had 147 compounds. We have divided into training and test using 75-25 division. And again, the training set is divided into sub-training and sub-test set. And we have optimized our settings for equilibrium distance, Gaussian and Laplacian kernel functions. And finally, with that setting, we have applied our read-across predictions for test set, and we have computed the validation metric values. We find from Gaussian kernel function, Q-square F1 value is 0.65, Q-square F2 is also 0.65. And this actually supersedes previous 3D QSR conform models also, and also the 2D QSR models. The third application in the COVID type work, although it is not ecotoxicity, we have used in read-across prediction for some FDA-approved drugs against SARS-CoV-2, not against some particular target. This is antiviral activity. So we have 44 compounds. We have divided into training and test, 33 and 11. So this 33 is again divided into two parts, sub-training and validation. And we have optimized the hyperparameters for sigma, gamma, number of close training compound, distance, and similarity threshold. And finally, we have optimized using the optimized setting we have applied on the test set. So we have actually used 4 different feature combinations, and we find that on the 4th combination, we get the best results. Q-square F1 0.932, Q-square F2 0.932, and this supersedes the corresponding QSR model also. Now about the quality of prediction and reliability of prediction, confidence of prediction, read-across predictions for data points for which you do not know experimental values. So we should have some available measures. So we have also worked on this, and we have suggested some measures like standard deviation of the endpoint values of the closed compounds, the absolute difference between the maximum positive and maximum negative values, and average similarity to the closed compounds, and a concordance measure, which is defined like this. And actually, the read-across prediction we can define in terms of 95% confidence interval as weighted average plus T95% into standard deviation of the weighted average divided by square root of n. So this gives us confidence of prediction. Actually, we suggested some measures also, which I think I have not shown here, to understand what is the quality or confidence of prediction. Actually, this analysis we have done using 3 different methods by comparing the different metrics for the high residual and low residual compounds using a t-test. We have also used a linear discriminant analysis to model the residual values. And thirdly, we have also used a sum of ranking difference approaches. And from that, we have found that standard deviation of the close similar compound, and the concordance measure G. These are the two important measures, apart from the other measures, for understanding the reliability of predictions. Our original work was published in Environmental Science Nano, where we developed the software, whereas, so this is the paper, whereas recently we have developed another technique where we can use these similarity and error measures, which are obtained from read across, and we can use them along with other descriptors in a quantitative RASA modeling, quantitative read across structure activity relationship modeling, which appears to be very promising, which actually supersede read across also and QSR also, but it combines features of both read across and QSR. And this we have applied in a particular androgen receptor binding affinity, and this is the first work for QSR modeling published recently. This is the paper where we have suggested different measures for the reliability of prediction for read across, and suggested different similarity and error-based measures published in Geometrics and Intelligent Laboratory Systems. And this is the work for the Falsomia Candida work, where we have shown the read across prediction can supersede QSR. And this is the work for repurposing FDA approved drugs for their anti-coronaviral activity, where read across can supersede QSR. So we thank our read across work. We thank ACRB for providing funds for read across work. And these are some of the reference text for QSR, understanding the basics of QSR for application in pharmaceutical science and risk assessment. The smaller version in Springer Brick, the primer of QSR modeling. The reference for application of QSR in drug design, predictive toxicology, and risk assessment. Application of QSR in pharmaceutical, chemical, food, agriculture, and medical science. These are some of the other applications in Alzheimer's disease, multi-target drug design, drug repurposing, and ecotoxicology QSR, and more two recent one against coronaviruses and in aquatic toxicology. Thank you very much for your patient hearing. If you have any question, I'd be happy to answer.
Thank you, sir. It was a wonderful session. I hope all the participants will get benefit from your lecture. So, with your permission, sir, I would like to open the question and answer segment. So, if any participant have any query, they can ask or put forward your query to sir, or they can put your query or questions in the chat box also.
Good afternoon, Dr. Kunal, sir.
Yes.
Sir, myself, Durga Prasad, Dr. Durga Prasad, working as an associate professor in Assam Downtown University. Sir, I have a few of the queries. Can you please clarify me?
Yes. Go ahead.
Sir, one first query is whether whatever the QSR you have enlightened us with the knowledge of yours, that was fine, but I would like to just have a small basic question, like whether it comes under molecular dynamics or molecular kinetics, sir?
It doesn't come under molecular dynamics and kinetics, because what you are talking about, that is the interaction of ligand with a receptor. So that is a structure-based design. QSR is not a part of structure-based design. You can use structure-based design information for developing QSR, that is a receptor-based QSR development. But whatever you are talking, that is structure-based design. That is the interaction of a ligand in a biological environment, in a dynamic environment of a receptor. That is a different concept. It is not QSR. So one should first make it clear, the basic understanding, before starting in UR. Molecular dynamics is nowhere related to QSR. This is two different concepts.
Yes, sir. The next query is there are many softwares which are available for us to find out the toxicities, like ADMET SAR, and even University of Melbourne, they have one toxicity studies. So what is the difference between the software which you have used and these, sir?
This is like, say, any QSR equation can be depicted like a model. In the simplest form, it can be an equation. Say, if you are developing an equation, then you have, say, a particular equation as I've shown, so y equal to a0 plus a1 x1, a2 x2, so on. So that is obtained from a particular training data, and also depends on your particular set of features that you're using for model development or particular method of model development. But in simplest form, say maybe an MLR. If we compare in the form of MLR, say you are using a particular set of training data, using a particular set of descriptors, so you get a model. If other people develop a model, if they have other training data, if they have other descriptors, so your X descriptors will vary, your regression coefficient will vary, your equation will vary. So I think one should be able to differentiate between two different equations with two different descriptor values with two different regression coefficients. So it is not a question of the software you're using. QSR is not a software. So QSR is a science that you apply on a given set of data with your knowledge of chemistry, biology, and statistics. So whatever software you're using, behind that, there is some science. Somebody has developed some equation with their background knowledge. But you are just a user. That's why your question is like this. What is the difference between two software? This question has no meaning because two equations will have two different characteristics depending on the training set data, the descriptors, the features, their regression coefficients. Two equations with two different statistics, two different features, set of features, two different set of regression coefficients will obviously different. Even with the same set of features, if you use two different training data, your models will be different. In that way, the two models will be different. Say, for example, for log P prediction, there are so many scales: A log P, log P98, C log P, M log P, X log P, all basically model hydrophobicity using some close related concepts, but their equations are different because they are considering the features in different ways. So their impact, the impact of individual features, regression coefficients are different. That's why their scales are different. You get my point? So when you use a particular software, particular algorithm, you always try to mention that because, as you know, according to OECD, your algorithm should be unambiguous. So whatever you use, a particular algorithm, particular model, if you do not know details about that, at least you specify that this is the version, because same model can vary from version to version also. Because if you say older version, some previous treatments may not be there. Or if you are using some expert system, their training data may have been enriched in later version. So model has changed. So prediction will change. Or it may so happen the previous version doesn't consider some particular element, say like iodine or some metal, but the newer version can handle that. So in that case, your prediction will change. The value will change. So you have to specify the version of the software that you're using. But lastly, I would like to tell that QSR is not a software. So it is used by people. If one cannot develop QSR model, then only one can develop a prediction system as an expert system as an user. So then one should use it as an user. You have to specify that this software, this expert system, this version, access date, this, and prediction value is this much. So there is no science. But to understand the science, you have to understand the basic theory of statistics of QSR model development.
Sir, my third query is that for predicted molecules also, can we go for this QSAR? What we are molecular docking and all those, we go for prediction. So is it applicable for this QSAR?
Probably you're trying to say that if you have some predicted values of some set of compounds, can you use this for QSR? Usually QSR is done from experimental values. You should know that molecular docking is mainly hypothetical because you are hypothesizing the interactions using different force field and all. But QSR is more experimental because for QSR model development, you need to use experimental values. And for validating QSR model also, you need to use experimental values of query set. So it is not recommended to use predicted values for QSR model development. And docking derived predictions should never be used for QSR model development. Because docking is itself a hypothesis. Docking derived prediction should never be used for QSR.
Hello. Hello.
Sir, thank you, sir.
Okay. Any participant have any more query? Okay, sir, I have received a query in the chat box. Can I read it out for you, sir?
Yes. Yeah.
Okay. So the question is, can in vitro and in silico data be used to confirm the similarity in the mechanism of action within a category or between the target and the source compounds?
Can in vitro in silico data be used to confirm similarity of the mechanism of action within the category or between? This is a very good question, actually. So whatever similarity aspect I have mentioned here, that is chemical similarity. That's why you will see in the title of my talk, it is chemical read across. But there is another kind of read across, that is biological read across. So based on the biological activity, biological behavior of chemicals, metabolism, toxicity, one can draw similarity consideration. So that is a large domain, biological similarity, and actually chemical similarity should be used in addition to biological similarity, and that will give more confident similarity consideration and more confidence in predictions. And one can also attach significance of predictions to various adverse outcome pathway, identifying the molecular initiating events, and one can also consider the multi-target consideration of drugs. Because when we administer a drug compound in body, it is not that the compound is interacting with only one target, it is interacting with several other targets also. So the propensity of interaction of a particular compound with interaction with several other targets and possible adverse reactions and their possible adverse outcome pathway and the molecules involved in those pathways in molecular initiating events, all these are very important considerations, and these are the future prospect of read across predictions and similar kind of work for application in drug discovery paradigm.
Okay, thank you, sir. I think the participants get cleared of their doubts. So again, I'm putting again, if anyone have any kind of query, you can put forward, or we can put to an end to this session.
So I hope this session is now concluded.
I think so that there is no more queries, so we can conclude it here, sir. So thank you once again, sir, for your valuable time, for sharing your work and sharing your knowledge with us. And I hope in near future we'll be again meet you in the offline mode, sir. Thank you so much, sir.
Okay, thank you very much.
Thank you, sir. And for the participants, the feedback link has been given in the chat box. You are requested to fill it up, and after filling it up, you can leave the meeting. Thank you.